is forecasting green building China. Is going to be ABEM-based and then
I'm very glad to attend the CIB 2022. Welcome to my presentation. My presentation is about the ABEM-based simulation of the building ingression safety for the elderly and the different circumstances, and it is the Enlightenments of the healthy residential building for the elderly. And this conference paper is completed by my supervisor, Professor Egression, and I will present this conference paper. So at first, let me introduce myself.
looks like really not perfect for them. So do you all hear me now? Is that good?
It's on, like, it is coming through. You just need to talk straight into it the whole time.
Do you hear me now? Hello?
They can hear you.
All good. So we are going to play the first video from Fan. Let's start now. Do you all hear the video? Do you all see the video and hear it well from online crowd? Could I have somebody to respond, please? Thank you. Thank you, guys. Yes, let's start.
Start.
Hello everyone. I'm very glad to attend the CIB 2022. Welcome to my presentation. My presentation is about the ABEM-based simulation of the building ingression safety for the elderly and the different circumstances, and it is the Enlightenments of the healthy residential building for the elderly. And this conference paper is completed by my supervisor, Professor Egression, and I will present this conference paper. So at first, let me introduce myself briefly. My name is Zhang, and I am a postdoctoral fellow in Department of Building and Real Estate of the Hong Kong Polytechnic University. And I have got my bachelor degree from the Shanghai University in China, and got my master degree from the City University of Hong Kong. And then I have got my doctoral degree from the Southeastern University in China. And during my PhD period, I have visited the University of Florida as a visiting scholar for more than 1 year. So the first section of my presentation is background, includes the introduction of my research and the brief literature review.
So generally, people spend around 19% of their time indoors, and the current mode of the working and the living have changed dramatically, especially in the post-pandemic era, when working from home and aging in place has become more common. So it requires the building should be flexible to adapt to different circumstances without compromising the occupants' well-being. And also, the population age has been regarded as a global issue in all over the world, owing to the declining mobility and functional impairment. The elderly have to stay at home most of the time, and the quality of life of the elderly mainly relies on the living environment. So how to provide a healthy living environment or the healthy building for the elderly should be considered seriously. So currently, large number of the old adults live in the mid-rise and high-rise buildings in high-density cities such as Hong Kong. And we should know that the built environment of this high-rise or mid-rise building is more complex than the single-family house, a townhouse, or some villa. So the elderly must meet more safety risks in this kind of the building. And most of the previous research focused on the apartment or homes, the risks in the homes. But we should know that the risks is not only exist within the residential unit like department and home, but also in the way of the building ingression and egression. At the bottom here are some news about the old adult risks in the fire and earthquake or some high urgent emergencies happen. So the first part of the literature review is about the healthy building. We know that many organizations has proposed or developed some standard or guideline for the healthy building, including the WELL certification of the healthy safety rating, and also WHO housing and healthy health guideline, and also Chinese evaluating standard for the healthy housing. But we know that this standard and guideline most focus on the all kind of the building, not just for the residential building especially, and also not focus on the elderly especially, and also this guideline or standard seldom focus on the egression safety especially. So the second part of the literature review is about the building egression and evacuation. We know that some researchers has used indoor walkability to assess the safety for the elderly, and also some researchers has contributed to develop the signage, the alternative route to building floor planning and other building elements affecting the egression safety. And also some other researchers mentioned that the elderly will face with more difficulties and risks during the evacuation. So here we know that the research gap is focused on the previous research seldom focused on the elderly and seldom distinguish the different urgent level of the circumstance. So the target of this research is aged residents, also called the old adults or the elderly, the seniors. And we just focus on the particular safety is that is building egression safety. And the scenario is we set as the circumstance with different urgent level, including the semi urgent level and the high urgent level. So the second section of my presentation is to introduce the research methodology, include the 5 steps to assess the building egression safety by the ABEM-based simulation. So in the right, here is a logic graph of the whole research methodology. I will introduce it step by step. So at first, step 1 in the green border, you can see here, determine the critical indicator of the egression safety for the elderly. So at the beginning of the study, setting appropriate indicator to assess the result of the simulation is required to reflect the egression safety quantitatively. So through the literature review, the critical indicator of simulation widely used in the previous study are adopted to reveal the egression safety, such as entire egression time and the safety margin. And furthermore, the new increment also we call the relative indicator, are proposed to reflect the egression safety of the elderly, especially, which is quite dissimilar to the ordinary resident. The increment in the egression time and the percentage of the later half egression from the general resident to the elderly can reveal the difficulty that the elderly suffer from during the process of the egression. All the indicator and the description is summarized in the table. So here we can see the absolute indicator we just extract from the previous study, includes the average egression time and the percentage of the later egression. And then the other one is a relative indicator. It's just an increment of the time and the increment of the percentage of the later egression. It's just compare the elderly with other residents to show their difference between elderly and others. So the step 2 is to set the scenario of the emergencies. Here we can see we have set 3 different kind of the scenario. One is a normal circumstance, and then the semi-urgent circumstance, and then the high urgent circumstance. The normal circumstance means the building operates in a normal condition and without any emergencies happen, and all the residents can move freely within the building under this circumstance. And then the semi-urgent circumstance just refers to some emergencies that will not affect the building condition and cause harm to the residents immediately. But the residents also need to leave the building within a certain time to avoid unnecessary harm. And then then is a high urgent circumstance is most severe, and this harm would impact on the building and the residents immediately and heavily. So under this high urgent circumstance, like the earthquake, the fire, explosion, and all residents should leave the building as soon as possible to save lives and reduce the injuries. Then the step 3 is to develop the ABEM for the scenarios. Here, the ABEM is the agent-based egression model. So here we can see in the logic graph, the ABEM includes 2 different parts. One is physical modeling, and the other one is logical modeling. And we use the software of the analogic as to conduct the agent-based simulation. The physical modeling is to build the digital building model in the software according to the basic information of the study case. And the field investigation of the residential building is required to collect the basic building information of the building environment and the residential egression habits which are reference for the basic setting of the ABEM simulation. And the logic modeling is to develop the egression logic for all the residents according to the basic characteristics of the residential actual behavior. Following the logic model helps to simulate the actual egression process in the software as much as possible. The process modeling library, the pedestrian library, agent palette, state chart, and the Java code are applied to build the egression logic model under the different scenario. But the detailed Egression logic model would be different with different residential building and different circumstances. So there is no standard logic model for all the study case. So since the residents generally egress the building through the elevator or the stairs, so here we just present the basic part of the logic model for taking the elevator and the stairs as shown in here. And the first one is taking the stair, and the other is taking the elevator to egress the building. So the next is step 4. After modeling the physical environment and egression logic and the different circumstances, the ABEM simulation can be conducted in the software of the logic. So in order to generate the enough simulation data, but also avoid generating a lot of the useless data, we just cite the standard simulation time for each scenario. So the ABEM simulation will last 30 minutes under the normal circumstances, and the ABEM simulation should be stopped once all the residents egress the building successfully under the other 2 urgent circumstances. So only useful simulation data should be exported from the software by setting the event, the variable, the data set, and the Java code. So we think the useful simulation data include the agent ID, the category of the agent, the departure flow, departure time, and the finish time. And based on the Java code, the events are executed to assign the values to particular variables and store all the assigned values in the data set. And then the data set are written into the Excel file when the simulation is finished. So at the last is step 5 is to analyze the simulation data. Since not all the data is helpful to identify the building egression safety for the elderly, so only the data related to the critical indicator mentioned in the step 1 is need to be retrieved from the software. So based on the original data, the value of the critical indicator can be calculated. The competitive analysis of the absolute value and the relative value are conducted to find out the egression safety of the elderly under the different scenario. So the last section is funding, including the case study, results, and contribution of this research. A common mid-rise residential building is shown as a case of the ABEM-based simulation. So this residential building has 10 floors and 4 apartments on each floor except the ground floor. And 2 stairs and 2 elevators are equipped in the building. So on the top is the floor plan of this residential building, and the next one is physical modeling in the software of the case study. The egression plan for this case is supposed as follows. In the normal circumstance, all the elderly and other residents live on the 5th floor or above relies on the elevator, while other residents live on the 4th floor or below can egress by the stair. When a semi-urgent circumstance happens, the elevator are reserved for the elderly, and all other residents need to egress the building by the stairs, and no matter which floor they live. And when the high urgent emergencies happen, it is unsafe to use the elevator to egress. So all the residents have to egress by using the stair. So here are results of the simulation. This is part 1 about the average egression time. So here there is a significant increment of the egression time of the elderly from the normal and semi-urgent circumstance to the high urgent circumstance. Due to the high randomness under the normal circumstance, the average egression time of the elderly under the semi-urgent or the high urgent circumstance shows more chiral relations to their living floors. Compared with other residents, the increment of the egression time of the elderly is not so significant under the high urgent circumstance, perhaps because the high density and the congestion restrict the speed of the other resident. But the egression time of the elderly under the semi-urgent circumstance has a significant negative increment on the higher floor, since the other residents living on the higher floor have to spend a longer time to walking down to the stairs. And then besides of total egression time, the sequence of the successful egression is also important to the egression safety as well. It is quite obvious that the elderly living on the average floor is likely to be one who egress lively than half of all residents under the high urgent circumstances, and this possibility of the later egression of the elderly significantly increases with the floor level, the lift. Differently, the elderly egress the building more quickly, but the possibility increase with the floor level under the semi-urgent circumstances. And furthermore, the percentage of the later egression of the elderly shows significant increment compared with the other residents under the high urgent circumstances. That means that maybe it means that other residents on the lower floor live in the building much earlier than the elderly on the same floor. However, under the semi-urgent circumstance, the percentage of the later egression of the elderly is similar or lower than other residents, which means that the elderly is less likely to egress late when the semi-urgent happened. So last here is the contribution of this research. This research integrated absolute and a relative indicator to assess the building egression safety for the elderly, and also considered the different performance under the different circumstances with the different urgent level. And also we developed the agent-based egression model to simulate and assess for the building egression safety. So my presentation is over. Thanks for your listening.
Thank you very much, Fan. Do we have any questions for her? Or online? Any questions? So it looks like we don't have any questions from the floor or online, but may I just ask you a couple of questions, Fan? Are you online? Are you with us, Fan? I saw her online before, maybe. Is she? Fan, are you with us? This is the most effective hybrid sessions, you know.
Yes.
Oh,
Thank you.
Hello. From Melbourne. I hope you're doing well there. So thank you for the presentation. And I'm just wondering, it looks like it's a very timely topic that you are researching on, healthier buildings for elderly. So it's a very good translational research. So what are the plans for you to translate this into real life situation? Are you planning to do any actual case study, data collection, and feeding them into models, or what's the plan for you?
This is always a theoretical simulation in the just some software in the analogic, but I think this the results, the simulation results can help us to optimize our evacuation plan or the evacuation route for the actual situation.
So in the model, you actually, one more follow-up question. Thank you for that. One more follow-up question. In the model, you actually simulated high-rise building, I guess, or multi-level. So what's the, if we were to do it in, for example, in Melbourne, our residential home care buildings aren't always similar to your case. What's the generalizability? How can we, is it easy to adapt it here?
Yes, I just choose just a very common residential building. I think there's multiple level residential buildings exist in all of the world. So I think I've never been to the Melbourne and Australia, so I think the as multiple level residential building is exists in most of the big cities. So I choose the 10 floor level, 10 level building for my case study to to help more actual cases in the world.
Thank you. One last chance for a question from the floor. If anyone has a follow-up question or no?
I noticed there is one question online.
There's one question online. Let me check. Thank you for reminding. All right, I think I can see. Okay, the question is, did you use some BIM model for this research? Monica has a question.
Yeah, that's a very nice question. This is also one choice for at the beginning of my research. I just plan to build the digital model in the BIM, which is quite widely used in all of the world. But I think this analogic is more suitable to conduct the agent-based simulation for this research. So I choose to conduct the simulation in the analogic. But I think the analogic can connect to the BIM through some plugin or some the other software. So in the further research, I will try to conduct more simulation or further simulation in the BIM model. Thank you.
Yeah, I think it's a very good, useful thought for you. Any other questions? No, if not, I wish you all the best for your research, Fang, and thank you so much. It's connected to our team in the conference as well, Building Our Future. So all the best.
Okay, thank you.
Let's move on to the next presenter. So the next paper is Forecasting Green Building Growth in Different Regions of China. The presenter is Linyan. Are you with us online? Linyan? That's okay. We'll proceed with the recording.
Hello everyone, my name is Linyan Chen, a joint PhD student from the Hong Kong Polytechnic University and the Chongqing University. I'm very glad to present our paper, forecasting green building growth in different regions of China. This is a collaborative work between the Hong Kong Polytechnic University and Tongji University. Energy consumption and carbon emission contribute a lot to global warming. According to the report from the United Nations Environment Program, in 2020, energy consumption in buildings accounts for 36%, and carbon dioxide emissions in buildings accounts for 37%. So in order to reduce the energy consumption and carbon emission, green building was proposed as an innovative construction product. World Green Building Council defined green building as a building in a life cycle that they can reduce or eliminate negative impacts and create positive impacts on the climate and the natural environment, preserve precious natural resources, improve people's quality of life. Green buildings spread fast around the world. For global market, LEED is the most widely used green building rating system in the world. There are more than 100,000 green building projects in 2019, a critical milestone for LEED and the global green building market. For Chinese market, China kept ranking second in the global LEED green building market. In 2020, green building in China has achieved more than 110 million square meters. So green building growth in China should not be underestimated. But there is a problem when we conduct empirical research to investigate green building development in China. From 2008 to 2015, we can collect the comprehensive data from the government website. The website stopped updating since September 2016. So from 2016 to 2020, we can't get all the data. And only a few governments, they can release the green building report every year. So it is a barrier for us to conduct the research. As for 2021 to 2025, the green building data is also unknown to all of us. If we can know the future data of green building development, we can help government, stakeholders, and practitioners to make effective strategies to improve green buildings in China. A prediction model can be classified into 3 categories: engineering model, statistic model, and artificial intelligence model. Economic activities are very complex. The engineering model and the statistic model, their ability to capture the complex relationship is weak. So more and more researchers tend to apply the artificial intelligence model because they can capture the non-linear relationship in complex problems. But traditional machine learning methods, their ability to process the time series data is weak. As a deep learning method, recurrent neural network can analyze the time-related sequence, which is a unique advantage in prediction. However, its accuracy would reduce when encountered the gradient vanish or explosion problems. To improve the performance, the long short-term memory model was proposed. The LSTM model can capture the long-term relationship in time series data, and the memory blocks in their network can access and store information for a long time. Because of this advantage, LSTM model becomes the primary option for time series prediction. Therefore, this study applied the LSTM model to predict the green building data in mainland China. Here is the research framework. This research includes 3 steps. Step 1 is data collection. Step 1 shows the input and output variables, which is based on our previous research. Step 2 is the data preprocessing, include data cleaning and data normalization. Step 3, it is the model establishment. Here is our LSTM model. We use an LSTM layer to capture the temporal relationship of various features among different years. Here is a typical module in the standard LSTM model. A self-attention mechanism is adopted to enable the model to selectively pay attention to different time steps, leading to better accuracy. After that, a dense layer is attached to extract the high-level representations, and then we use another dense layer to regularize the prediction dimension to keep the same size with output. Because of the data of input variables ended in 2020, this study needs two different LSTM models. The first one was trained to forecasting the input variables from 2021 to 2025. And the second LSTM model was trained to forecast the output variables from 2016 to 2025. So we can predict the certified green building number from 2016 to 2025, 10 years in total. These two models apply the dynamic prediction process, and the time step is 5 years. We use the mean absolute error and the mean absolute percentage error to discuss the model's performance. The first one indicates the difference between the true value and the predicted value. It is acceptable because green building in China increased significantly in these years. So the difference is not obvious. The second one is relatively high, but it still can be interpreted. In the primary stage of green building development, the green building is a small number. So once the error existed, it shows a large percentage. After we delete 5 outliers, it reduced to 28%, which is acceptable. This figure shows the trend of green building development in mainland China from 2008 to 2025. The data of stage 1 are from the government website. It is the official statistics. The data of stage 2 and stage 3, they are the prediction result. We can see that there is a moderate increase in stage 1, and stage 2, it begins a rapid increase, although there is a plateau in 2016. But it resumed a quick takeoff from 2019. So the results show that green buildings will keep the rapid increase in the following years, and a decrease will appear in 2025. This study applied the K-means clustering to investigate the spatial patterns. Regions are classified into 4 categories. Dark green means more green buildings. So we found that the green buildings in China gathering in the coastal areas. The difference between categories are significant, and 22 regions gathering in category 4. So we conduct another K-means clustering and found that green building performance of central regions is better than the western regions, and the inland regions adjacent to another countries. So this study have 3 conclusions. The first is that the enhanced LSTM model performed well in predicting green building growth. Green buildings in China has a significant increasing trend in these years, and the growth rate will be much higher in the future. A 3-step spatial distribution pattern is observed, and significant gaps exist between the developed regions and undeveloped regions. Okay, that's all. Thank you for your attention, and I welcome all questions.
Thank you, Linyan. Are you online now? Do we see you here? Yes, she's available. So do we have any questions? some people? We do not have any questions from the floor, but online, do we have any questions? Looks like it's very informative and self-explanatory, and no questions from audience yet. I would like to ask you a question. So your prediction in 2021, the third stage predictions that you had, are you in a position to go to that graph? Are you able to share the graph that had the prediction curve?
Sorry. Good morning, everyone, and thank you for your question. Please repeat your question because if you are not close to the computer and the sound is very small.
Sorry about that. Do you hear me now?
Yeah, I can hear you now.
All right. I was referring to your results that you showed in one of the slides. The curve.
Hello?
Do you hear me online? All right. So, okay, I'll repeat my question.
Okay.
So, the prediction that you did from 2021 onwards.
Yeah.
Do you have any explanation as to why in 2024 it comes to a peak and then drop afterwards? Why do you think that would happen?
Oh, I think in green building in our channel, we just keep the rapid increase, but the increase is not always stable, and it will come to a decrease because the buildings, the total of the building is limited, so we can't always keep the high grades, I think. Thank you for your question.
I have one more question for you. In your model, so the original, we have two snapshots of data, isn't it, from 2000. But the gap between those two were like 8 to 10 years, 5 to 8 years. Am I correct?
Yeah, I use two LSTM model. One is to forecast the output variables because in 2021 to 2025 our input variables are unknown, and I use another LSTM model to forecast the output variables because output variables is unknown for us from 2016 to 2025. So that's why we use two different models.
All right, okay, that explains. So if you have every year data, do you think that will help increase your validity, the accuracy? For example, from now onwards, how do you think it would affect?
I think it is good. It is a good things for the green building development in China, and I think our research can place a solid foundation for the following empirical research and can provide other reference to other researchers or government or other practitioners.
Oh, that's a very good point you mentioned. The potential stakeholders also would benefit from your study. So what's your plan after this stage?
Actually, the following research, we are now conducting the following research to use the forecasting data to conduct another empirical research and analyze the spatial patterns and the future trend of green building in China. So I think it is a good beginning.
Yeah, that's great. So spatial patterns, including it, that's really interesting area as well. Well, thank you very much for the nice presentation and answering the questions. Do you have any questions? Last one more question, maybe? Yeah. So thank you again, and all the best for your research, Linyan.
Thank you for your question, and I'm sorry that I can't hear clearly in the middle of our Q&A question. Thank you.
Can we move on to the next please? I think the third presentation we have to skip because the presenter didn't make it publicly available and we are not in a position to play it. So I apologize for that. If you have any questions for him, I'm sure you can email. So we are coming to the last presentation in that case. So the title is Building Typology Prediction in Smart Cities. And ACR is the presenter. Are you with us today online? ACR, are you with us? That's okay. Let's watch his presentation.
Welcome everyone. In this presentation, we are going to review the work we have completed for building typology prediction in smart cities. First, we're going to see a brief introduction of this area. Then we are going to briefly explain the theoretical basis of our work. Then we are going to present the materials we have been using during these months. Later, we are going to show the experimental part and the results we obtained. And finally, we are going to see some possible future work lines with this work. Well, digitalization of cities is a dynamic process that is evolving ever faster as a result of the advances in fields such as artificial intelligence, robotics, the Internet of Things, connected vehicles, 3D printing, and energy, thus improving citizens' lives. A smart city model consists of different subsystems in which we can highlight both smart buildings and smart sensors. In these models, it could be of special interest to know the movement patterns of pedestrians to predict and act in real time. For these purposes, there are large open source data available, and using data from cities of Melbourne and Madrid, our approach divides different types of sensors following different criteria. First, we conducted an exploratory analysis of the data from the previous dataset in order to know if all sensors have enough information to include them later in PC analysis and clustering. With the PCA, we analyze the cumulative explained variance of different numbers of components for each dataset. After scaling the data with means 0 and a standard deviation of 1 for each attribute for optimizing the results, in our case, we established 95% of variation to be explained by the number of components selected. Later, we grouped these sensors depending on the number of each type of buildings surrounding them, or the early mean activity throughout different days of the week. Using as features this data, we grouped the devices following K-means algorithm after establishing the optimal number of clusters following the elbow method. The function inertia simply computes the square distance of each sample in a cluster to its cluster center and sums them up. The smaller the inertia value, the more coherent are the different clusters. So when as many clusters are added as there are samples in the data set, then the inertia value will be 0. After obtaining principal components, we proceed to apply the K-means algorithm after evaluating the optimal number of clusters according to the elbow method. The point in which the graph flattens will indicate the optimal number of clusters, just enough to achieve a desired difference and coherence between clusters. After grouping this sensor into different clusters, you use different types of supervised machine learning algorithms to validate the goodness of the clustering processes carried out in the previous phase, using tenfold cross-validation to validate them. These were the typical performance measures we used to evaluate the clustering processes. You use the information available in the pedestrian counting system sensor locations dataset to carry out this. After all, we removed the instances from sensors which had not been operating. Then, we decided to establish 2-hour time intervals for each day and separate weekdays from Saturdays and Sundays. By this way, we generated a new dataset named Melbourne pedestrians with mean hourly count data final all that included the mean hourly count value for each sensor in different time intervals of different days, weekdays, Saturday, and Sunday. Similarly, we counted the buildings that were under a previously defined distance, 300 meters, from each sensor, obtaining their location from pedestrian counting system sensor locations dataset and buildings with name dataset, and these countings were used later to perform a PCA and a posterior clustering of sensors depending on the typology of the buildings nearby. These results were summarized in a new dataset named Melbourne count pedestrian buildings that had been used in the posterior phases. What we obtained after clustering following the criteria of building typology nearby these sensors, we can see that there are 3 very clear clusters and some others that may not be so easily distinguishable. And we have the same thing for the other criteria. There are 2 clusters that may form a new only one cluster, that is the cluster 1 and 3, and there is an outlier that we remove after all the processes of validation. And finally, we validate these clusters following the cross-validation process with 10 false and for different seeds. In this case, 30 different seeds. This is the case of the criteria of building typology, and we can see that the best validation or the best classifier in this case was AdaBoost, using a seeds root or a seeds classifier, the random forest. In case of the criteria of mean hourly activity, we have these results, and the decision tree is the one that obtained the best performance metrics. And finally, we performed Kolmogorov-Smirnov test to know the normality of the means of performance metrics. You can see that the statistics and p-values are very streamable, and in both cases, we have to refuse the null hypothesis, saying that performance metrics are not drawn from a normal distribution. Similarly, we performed the Kruskal-Wallis test to see if those performance metric means come from the same population or not. And in this case, we can say that all means does not come from the same population in both cases. And finally, to compare the clusters from both criteria, we can say that sensors that were forming the clusters of retail, for example, were more or less in the cluster of weekday and weekend. In this case, because the sensor activity of this type of buildings, for example, of retails, is high during all the week, and it's lighter or less significant in weekends in case of the sensors that were grouped in the office cluster, and the sensor, for example, that were grouped in the residential apartment or house cluster, their mean hourly activity were much more significant in weekends. All this makes sense and supports the work we have done, because by this way we can differentiate or deduce the type of buildings that are that sensor are located, only knowing their mean hourly activity. Now we have the possibility to repeat the same process of clustering with data from Madrid, with a higher number of sensors, and we had the opportunity to prove our clusterings and to expand these clustering processes. We could introduce also graph-based clusterings using as node sensors and using as weights of or the connections, the inverse of distances between sensors. And we can also consider using convolutional neural networks due to their power in this type of tasks. So this is everything. Thank you very much. See you soon.
Thank you very much. Do we have questions? Any questions from the floor or online?
There's more value at Coles with 20.
I have a very quick question for you. So it's an interesting study. I'm sure you selected the. Is you online? Yeah, probably that's fine. So that concludes our session with the presentations, and let's thank all the presenters, those who are here or not with us today. And also thank you very much for joining us, for the crowd on site. I know it's early morning, still yet to wake up some of you, and some of you are jet lagging. And again, I extend my warm welcome to all of you to Melbourne. Have a nice time in the conference, and all the very best for all of your research. Jeremy? Hello? Jeremy, do you hear me?
Hello. Jeremy, do you hear me? You there? So it's my apologies that your presentation couldn't be run today because you have set it private. And I think you still can upload it as public and people still can view it. So yeah, so I think that's the best solution we can do. You can re-upload it as public and we can make sure that it's available for everybody to access again and ask any questions if they have. Thank you.